here is the line integral. The integral, hopefully you know that is you follow the ds, and that basically is the path throughout the whole circulation. Okay, so we can manipulate the whole thing here. And this one, again, tau t and p ds, and tau t basically is q, and that is a constant. We can take out of the integration here. What is ps? We look at the geometry here a little bit. ds is this dimension.
Yeah.
Okay. I think more appropriate is, I think, follow up the textbook notation. I think the textbook simply, because the thickness is varying across the path, I think the textbook using the ds is taking the middle, which is simply follow our textbook notation. So ds is the dimension and the middle, so that could be the average of the two sides, for example. Okay, so ds is here. So ds is here, and then multiply p. What that mean? You look at here. So if this is a small ds, and this is a certain point,
like it's a triangle?
Yes. So what I want to say is, you can see the ds multiply p, which basically is about the area of this corresponding triangle times 2.
Corresponding triangle times 2.
Sorry, the p times ds will be equal to the triangle's area times 2, right?
Well, but it's...
Or...
Oh, base times
Right.
Oh, yeah, okay, that's where you get the 2. Okay,
Okay, very good. So let me draw the triangle here. So the triangle is like this. So this is triangle. Okay. So basically here we trying to do is this. This is the small triangles. We simply integrate so many pieces of the triangle across the whole path. So if we have kind of stacking all the small triangles piece by piece together, basically we do the line integral that indicates the whole.
But why is it... Okay, so I get like that it's a triangle, but isn't it the distance between where they cross in ds that would be the base of the triangle? Because ds isn't really
ds is a base, and p is a height.
But it's not a right triangle.
It's not right triangle.
Yeah,
So here the ds is a base, and p is a height. So base multiply height divided by 2, that is the area of the triangle.
Doesn't have to be one triangle.
Okay, never mind.
Hit her. Okay. So basically this is the 2 times of the, let me put a small triangle. Okay, so that's meaning. So once we do the integral of this one, then you can see we take the q out. So we do the integral of those small triangles. We take the infinitesimal summations of small pieces triangle. Would that be equal to this one? So then you redraw this one again. This is a cross section, and with the varying thickness. So this is a middle line. Follow up the path. You can see this integral, that meaning we take the summation of small pieces of such triangle together, so that meaning is in this area. Are we okay? Sarah said yeah, I think everyone should be yes. Okay, so this one, this area, we defined the A, and that is a symbol here. Okay, so this one is the area C below. Okay, and for very thin wall, and really it's not critical if you not to take the middle line, but we simply follow our textbook because that would be we simply pick our standards. So in this way, from this point onward, I would say for all the calculations, we simply take the middle line of any thickness and then using that kind of enclosed area as the A. We'll build up the standard and then we'll follow up those things. Okay, so that is the first one here. So with this one must be equal to T in moment equilibrium. So that means we have this one here. So from the first property, we say the Q shear flow is constant, and what is that constant? Basically, it's equal to this one.
So you just proved it.
Not prove it, to calculate for certain calculation. I simply keep your result, keep the result.
I mean, well, like what you initially stated as the property, you just
Yeah.
proved in the integrals, the line integrals.
Sometimes I would say keep the result first and then don't lose it.
Oh, well then, yeah.
And so that is for the second one. So in here with these quantities, we might be able to calculate the shrink stress everywhere. As long as you identify any segment, you measure the thickness, then you can quickly calculate tau over there. Okay, so that's the one. The third one, I want you, and also last one is, I want to relate the torque and respond in response to I want to find to calculate the angle of the twist in response to the torque. Okay, so maybe next page. So again, this page here is A. That is the symbol used in our textbook. So we see what is the next page of my slide. Okay, so this here, we can quickly go over here. So that is for the first properties, and this is for the second properties. Sorry, here here's supposed to be a circle, and for the line integral, because I use the different the software called the mass type. I didn't use the Microsoft Office, so here kind of give a little bit weird symbol here. The third one, the angle of the twist, and that is the third property. And maybe I